Hey everyone, welcome. Today we're going to crack a classic coding problem, one that you see all the time in technical interviews. Now it seems pretty simple on the surface, but trust me, it's a fantastic lesson in how to write efficient, clever code. We're talking about the valid anagram problem. So, to get our minds warmed up, just take a quick look at these two words, listen and silent. Are they anagrams of each other? I mean, they've got all the same letters, right? Just shuffled around. The answer is a big yes, and our goal today is to teach a computer how to figure that out for any two words you throw at it.
And here's the official definition we'll be working with. See, it's not just about having the same characters. The key phrase here is exact same frequencies. It's about having the exact same number of each character. Listen has one L, one I, one S, and so on. Silent, well, it has the exact same count for each of those letters. That's the heart of the challenge.
All right, here's our game plan. First, we'll look at the simple solution, the one that probably comes to mind first. Then, we'll see why it's not the best and uncover a much more efficient method. We're even going to throw in a little curveball that interviewers just love to ask. And finally, we'll wrap it all up with the big lesson here.
Okay, let's dive into our first approach. This is usually the first idea that pops into your head when you hear the problem. It's the intuitive way to go.
So this is probably what you're thinking, and you know what? It's perfectly logical. First, the easy check. If the words have different lengths, no way they can be anagrams. Done. Then you just sort the letters of each word. If they're anagrams, they should end up looking exactly the same, right? Listen becomes E-I-L-N-S, and silent also becomes E-I-L-N-S. Bam, it works. But, and this is a big but, here's the catch. This is what separates a good answer from a great one in an interview. Sorting, while it gets the job done, is what we call computationally expensive. We measure this with something called time complexity, and sorting is O of n log n. Now, all you really need to know is that this means the longer the words get, the disproportionately longer it takes to solve. So the interviewer's always going to ask, can you do it faster?
And that's our challenge. Solve this without sorting. This forces us to think about the problem in a totally different way. Instead of worrying about the order of the letters, what if we only cared about the quantity of each letter? This leads us to a way more elegant solution, the frequency count. I love this analogy. Just think of it like you have two bags of Scrabble tiles. You don't need to actually spell the words out, you just dump them out and count the tiles. Does each bag have the same number of A's, the same number of N's, the same number of G's? If all the counts match up, you've got yourself an anagram. It's really that simple.
And here's why that little shift in thinking is so huge. The frequency count method runs in what's called O of n time, or linear time. That just means the time it takes grows in a straight line with the length of the string. For really long strings, the difference between O of n and O of n log n is absolutely enormous. This is the kind of optimization that really impresses people.
Okay, so let's break down how this actually works. First, we do that same easy length check. Then, we make a super simple array with 26 slots, one for each letter of the alphabet, all set to 0. Now, we loop through our strings just once. For every letter in the first string, we add 1 to its slot in the array. For every letter in the second string, we subtract 1. If they're perfect anagrams, every +1 will be canceled out by a -1, and our whole array will be full of zeros at the end.
Let's walk through it with anagram and nagaram. So, as we go through anagram, we increase the counts. The slot for A goes up to 3, N goes up to 1, and so on. Then, we go through nagaram and we start subtracting from those same slots. And what happens? Since they're perfect anagrams, every single count goes right back down to 0. If there were any numbers left over, we'd know instantly it wasn't a match.
Okay, so our solution is looking pretty solid, right? Fast, efficient, but now, for the twist. A great interviewer will always ask a follow-up question to test the limits of your solution. What happens when we're not just dealing with simple lowercase English letters?
For example, what happens if our strings have Unicode characters, like emojis or letters from other languages? Our solution, with its neat little 26-slot array for the English alphabet, would just, well, it would completely break. It has no idea what to do with a smiley face.
And that's the thing. Our fast, elegant solution has a major blind spot. It's built on the assumption that we're only ever going to see lowercase English letters. The moment we step outside of that very specific box, it fails.
And this brings us to a classic trade-off you see all the time in programming. To handle Unicode, we need a more flexible tool. Instead of our fixed-size array, we can use something called a HashMap. Think of it like a dictionary, where the keys can be any character.
a Cyrillic letter, an emoji, whatever, and the value is its count. It's incredibly flexible, but there is a small cost. Its memory usage isn't fixed anymore. It grows depending on how many unique characters are in our strings.
So after going through these different approaches, let's pull it all together. This whole journey from a simple idea to a more complex one reveals a really important lesson about programming. It's not just about finding an answer, it's about understanding the right answer for the situation you're in.
You know, great programmers are always thinking about edge cases, those weird, unusual inputs that might break their code. So what if the strings have different lengths? Yep, our first check handles that. What about empty strings? Our logic correctly sees them as anagrams. And what about words like rat and car? Same length, but different letters, so our frequency count won't end up at 0. Our solution handles all of these scenarios perfectly.
And this really brings us to the most important takeaway of the day. The goal wasn't just to solve the anagram problem. It was to learn how to choose the right tool for the job. If you know for a fact that you'll only ever see lowercase English letters, that simple array is the fastest, most efficient choice. But if you need to handle anything the world might throw at you, the HashMap is the way to go. Recognizing those trade-offs, that's the mark of a great programmer. So, I'll leave you with a final thought to chew on. Now that you've seen this pattern, this shift from thinking about order to thinking about frequency, where else might it apply? What other problems out there that seem to be about arrangement are actually just problems about counting? Keep an eye out for it. I think you'll be surprised how often it shows up.